Oh,
You're late.
a wizard is never late. Or early. He arrives precisely when he means to. My wizard hat seems to be falling off. My wizard beard, though, that is on tight. Hello,
Straight
young
up.
hobbit.
Gandalf.
Are you Bilbo or Frodo? I'm old, I can't tell.
I'm more closer to Frodo's age, but actually I would consider myself a young Frodo.
I guess it depends on at what point in time does this lesson on trigonometry take place. I'm here, though, to teach trigonometry. It's important in every young hobbit's life to learn about the unit circle.
Your Gandalf voice sounds really similar to your pirate voice.
Arr, what are you talking about? Wait for it. I'm gonna do some location magic. Boom! I'm in a new location.
Whoa. Amazing.
You are still in your hobbit hut.
In my hobbit hole? I'm in
hobbit
Hobbiton.
hole.
But actually, I found this ring, and I don't know. I wonder what happens
Go!
if I put it on.
Where did you go? Oh my gosh!
I can hear you.
Wait, I'm Gandalf. I know what's happening. That's the one ring.
Oh no! I guess we should really quickly do this assignment, and then I can take it off and not get attacked by Nazgul.
Wait, is that one in the background there? No, I don't think so. I think that's just Samwise. Oh, Samwise. All right. I believe I'm sharing my screen. Hey, can you see the trigonometry?
I can, but it's kind of small. Can you make it full screen, perhaps?
Wizard magic. Pow!
Amazing.
This Gandalf the newspaper, has digital powers.
Wow.
Digital age of Middle Earth.
That's,
You kind of sound like a pirate. Anyways, apparently Mrs. Contreras and Mr. Kirk, not us at all, taught last time about radians, the arc length on a unit circle, a way to measure the span of an angle, and also the unit circle and the wrapping function. Interesting. Wrapping strings around circles. Is that even math? When we got to this thing, or they got to this thing, the unit circle. How beautiful. Is there anything you want to recap before we begin here?
I think the we can just soak in the how lovely that looks. There's so much symmetry happening, and don't concern yourself that it vaguely also looks like the great eye of Sauron. Just don't.
Oh, it kind of does look like the great eye of Sauron.
Now that I think about it.
You are always being watched by the unit circle. Oh man. All right, let's continue on our journey to understand trigonometry. Maybe we'll destroy a ring at the end of this.
Ooh.
All right. So, we left off talking about the unit circle. Today, we plan to connect the unit circle to what you might already know. Sine, cosine, and tangent. And Mrs. Contreras, do you remember what sine, cosine, and tangent represent?
Those are the ratios of like sides for only, I think, right triangles we can use those.
Mm-hmm. Given an arbitrary angle.
Bam!
Oh, you grabbed it. That reminds me, I have a surprise for you, Mrs. Contreras, and I've been holding it a secret for many a score.
Oh, well, this crab has a ring, so it's gonna disappear.
Well, I've stopped sharing because we've recently done an art project in our Precalculus class. And I did not make it because I'm Gandalf, the newspaper. But Mr. Kirk made you a piece of art.
Wow. Oh,
Do you know how many
lovely.
crabs are on this piece of art?
I think more than I have crabbed you.
This crab is half the size of this crab. And this crab is half the size of this crab.
Whoa.
And there are an infinite number of crabs on this piece of art.
So I can never out crab you now.
I have just infinitely crabbed you. I'm
Oh. That's just overwhelming. I think I need to disappear for a while.
I've been waiting not weeks, a week to give that to you.
That's
I will
incredible.
physically give it to you when we return to school.
Wow, thank you,
Return
Mr.
from
Kirk.
Mordor. All right, back to what we were doing. I was
think
wondering how I would slide that in somehow.
how you would crab me.
How would I infinitely crab you? Boom. All right, we're back. You talked about ratios before crabbing me. Regardless of the size of this triangle, given an angle, this kind of looks like. Oh, wait,
Wait, that is forbidden.
Ah,
There you go.
yeah. Given an angle, the opposite side over the adjacent side will always be the ratio. The division between these two things will always be the same, regardless of how large the triangle is. All right. Do you know of a mnemonic device to remember sine, cosine, tangent, cosecant, secant, and cotangent?
The mnemonic device that I like is somewhere far, far away from Middle Earth. It's a tropical island. Some call it Sokotoa.
You know, I think of that Finding Nemo. Every single
Shark
time.
bait. Wah.
Shark. Sokotoa. Sokotoa.
Here.
An island far away from Middle Earth.
Soka.
Oh,
It's gotta
yeah,
be
not,
an A.
not SoCo.
Soka.
That's a place in California. Probably not, actually. That'd be SoCal. Anyways, this is Sokotoa. It kind of rhymes. All right, so what is this telling us, though? What does this mnemonic device reveal to us?
That for sine, we have the opposite side length over the hypotenuse. So with our reference angle, we have an opposite, a hypotenuse, and an adjacent side.
I'm waiting for it to drop. Boom!
It's a very
O
bad-
A H, and you know I'm going to go ahead and use the terminology that you're using, the symbolism you're using. O over H. All right. Why is it called sine? We'll actually reveal the etymology of why it's sine and cosine and tangent later on. But for now, sine. All we need to know is that it's opposite of a hypotenuse. Let's fill out these other ones. Cosine.
Cosine is ka,
Over.
so
Tangent.
adjacent over hypotenuse, and tangent is toa, so opposite over adjacent.
And how about these three down here?
Those use the wrestling move reciprocator. And so you take the reciprocal of sine for cosecant, you take the reciprocal for cosine for secant, and you take the reciprocal of tangent for cotangent.
And this is the sound that you make when you reciprocate. Hoo, ha, ow! I'm sorry, everyone. But this is not my fault. This is not Mr. Kirk's fault. It's Gandalf, the newspaper's fault. All right, so we have those. We have that prior knowledge behind the Sokotoa. It's just it is a function, a set of functions that represent the ratio given an angle. Given the angle pi over 6, what is the fraction of the opposite side over the adjacent, for sine, opposite of a hypotenuse of the sides of a right triangle?
Mhm.
The angle changes, the value changes. Here's a good question. What's the maximum value for sine?
The maximum value for sine
In a
is-
triangle. In a triangle.
Oh, in a triangle. Okay, so it's
Right.
like you can't have your opposite over the hypotenuse to be anything more than 1 because your because of the what's it called? It's like the triangle inequality or something.
You have the triangle inequality.
Or you
I don't know
have,
if that's technically the triangle inequality, but our hypotenuse is our largest side, right?
Mhm.
The largest side is opposite the largest angle, always in a triangle. So we can never have a side, a leg larger than a hypotenuse. So our fraction is always going to be something smaller than 1. O will always be less than H. It's always going to be less than 1. It could be as small as just more than 0 and as large as just less than 1. Maybe it can be 1. Maybe it can be 0. Maybe we need to redefine our sine function for real numbers and not just the triangle. Let's proceed.
Gandalf the beard. I think your beard is causing a lot of microphone sadness.
Don't worry, I have another beard.
The second beard.
The second beard. Yeah. Oh, let me know if it gets a lot. No, it's cracking.
That was bad. All right.
I've been my identity has been foiled. It's like Santa Claus at the mall. Santa Claus is real, sorry. Anyways. Now let's redefine our trig functions so that maybe they don't have to rely on the triangle. Right. Let's look at the unit circle and calculate the following trig values for the angle pi over 6. We're up here.
Okay.
We have the angle pi over 6. And we want to calculate the sine of pi over 6 according to that faraway island, Sokotoa. What is sine of pi over 6?
I think, well, the opposite here is 1/2. And the hypotenuse, because we're on the unit circle, is a 1. So we have a 1/2 over 1.
So 1/2 over 1, that is 1. Can you write that on the next page for us?
I can.
Cool. So we have 1/2 over 1. And if I were to dilate this triangle by a scale factor of 2, I would have 1. Maybe it gets twice as big. This is the idea of Sokotoa. Regardless of the size of the triangle, opposite 1 over hypotenuse 2, it's still going to be 1/2. Right, so the sine of the angle pi over 6 is 1/2 over 1, or 1/2. I believe it asks for pi over 4 next.
It does. Sine of pi over 4.
Sine of pi over 4, what on the unit circle is the sine of pi over 4?
It looks like it's a 1 over root 2.
1 over root 2. I'm going to write root 2 over 2 because that's what I like. I know you like 1 over root 2.
Yeah.
Hypotenuse, still 1.
Over 1.
Wait, time out. And then the pi over 3. The hypotenuse is still 1. We're always just dividing by 1.
So can we just use the y-coordinate
I think we can.
for sine of pi over 3?
Sine of pi over 3, that's root 3 over 2.
Root 3 over 2. Bam. Bam.
Root 3 over 2. The sine, well, you just answered this next question. In each case, what is the sine of an angle? On the unit circle, the sine of an angle, because we're always just dividing by the hypotenuse, the sine, I'm going to write this. You got it, sorry.
Y value.
The y value, yeah. The sine of an angle, if we reinterpret it to look at the unit circle, is just the y value on the unit circle. If I, instead of saying, what is the opposite over the adjacent, let's just get rid of triangles and say, it's the y value. We're always going to divide by 1. Let's get rid of the hypotenuse and only talk about the leg. Let's define sine not based on any triangle, but specifically the triangle nested inside the unit circle. Cosine of pi over 6, that's adjacent over hypotenuse.
So wouldn't
Hypotenuse
that
is always
be-
1.
And so we have 3 over 2.
Root 3 over 2. Now I'm doing like Darth Sidious, like electric force.
Oh man, we need to do another Star Wars.
Yeah,
theme.
I know we do. Oh, my cloak is apparently coming off, which is just a blanket. Cosine of an angle, the hypotenuse is always 1. So adjacent over hypotenuse, adjacent over 1, adjacent is the x value. Let's redefine our trig functions as coordinates on the unit circle, because our hypotenuse is always 1. Cosine of pi over 4, Mrs. Contreras is saying, root 2 over 2. That is the x coordinate on the unit circle of the angle pi over 4. Cosine pi over 3, I'm going to go a little bit. That's going to be 1/2.
And why? Because that's the x value
No,
for
x.
that location.
Sine is the y value on the unit circle. X is the cosine value on the unit circle. Because it's a unit circle and our hypotenuse is always 1. Down here, we will now expand our definitions of the trigonometric functions above to apply to any angle, even angles. My hat has fallen off. You know, to keep the theme,
like I should,
take the hat off.
I'm
Going back. Going back. Oh, I'm back.
Oh.
All right.
Welcome to our homepage.
I should make yours my anyway. Let's not get too into it. We're now going to expand our definitions of the trig functions to apply to any angle. It can be bigger than not 180, but pi radians. We're trying to get rid of that other unit of measurement for angle span. We can have angles because we have the unit circle, and the unit circle is defined for all real numbers. The wrapping function is defined for all real numbers. So like, what's the sine of negative pi over 6? If we establish the sine of an angle to be the y coordinate on the unit circle, negative pi over 6 is down here. What's its y coordinate?
Negative 1/2.
Negative 1/2. So we can now, if we redefine our rules for trigonometry, we don't have to deal with a right triangle that only has positive values. We can deal with negative things as well. Let t be a real number, and let t map onto the circle using the wrapping function. We define the following 6 trigonometric functions as follows. We define the 6 trigonometric functions as follows. And fun fact, there are more than the 6. Maybe we'll talk about those later. There are only 6 that are.
In a cinch.
Yeah, well, yeah. And there's like one called like there's a cool picture. Maybe I'll find it before the end of this video. All right. Or maybe people can check out the other trig functions besides the 6 that we normally talk about. Write about in your journal.
Journal.
All right. So sine we just defined. The sine of a number is the y coordinate. What would that make the cosecant of a number?
The reciprocal of y?
Yeah, like this is y over 1, right? And this is going to be hypotenuse over opposite. But this one we can get rid of. This one we can't get rid of. So like the sine of pi over 4, that's root 2 over 2. The cosecant of pi over 4, that's going to be reciprocated, which I believe is just root 2.
Which is why I like not rationalizing the denominator.
Yeah, because, yeah. All right. 1 over root 2 and then just root 2. There's a nice relationship
exactly.
there. Yeah, I
It's
got
just
you.
there.
Cosine?
X.
X, which makes secant
1 over x.
1 over x. I don't have a good way to remember which of cosecant and secant go with its previous function. I have a good way later on, but when first teaching it, I don't have a good way to relate the two. Do you have a good mnemonic device?
You just want to make pairs of your c's and s's.
Make pairs of c's and s's.
Right, so you want an s and a c to go together and an s and a c to go together.
I like that a lot. There's a reason why this is called co, and we'll talk about that later. Of course, everyone can figure it out beforehand if you are impatient. And the last but not least, the tangent of a function Wait, let's go up to our unit circle. If I said, hey, what's the tangent of pi over 6, what would you say?
That would be 1/2 over root 3 over 2.
1/2 over root 3 over 2. So there's no real getting rid of anything here. There's no real getting rid of a hypotenuse. I think we need to just like keep it y over x. And then the cotan would be x over y.
Oh, hang on a minute. Can you go back up to the unit circle?
Yeah.
So if we take the 1/2, I'm going to try to make this not look like barf. But if you take this 1/2, and that's our like first number, and we're taking it over this root 3 over 2 second number.
I can't see anything yet. Are you drawing on the unit circle page?
I am.
Okay,
Do you
cool.
see the greens?
I do see the greens now, yeah.
If I take the verticals part and I just pull it over, so I make it more look like that. Bam. And then I have, so that's the first number divided by that number. Boom.
Oh, I think I see what you're saying.
Is there any connection between this line that we have and that number that we just got? That tangent?
I'm adding something to the page myself. Rise over run, right?
So that's the slope then.
That's the slope. The tangent is the slope. I think we've said this before. And because it always, when we're talking about tangent, our initial point is the origin, and our terminal point is on the circle. So the slope is truly just y over x. Tangent is the slope on the unit circle. So what is the slope here then? 1/2 over root 3 over 2. I'm going to do it here on the side. 1/2 over root 3 over 2. Some chops.
Chop, chop.
1 over root 3. We could leave it like that. I do want to rationalize because that number makes a little bit more sense to me.
Okay.
Root 3 is about, I believe, 1.7 divided by 3. That's going to be like 0.5 something. So that slope is probably around between 0.5 and like 0.8.
Okay.
I don't know. That's why I like to rationalize. That's one of the only reasons why I like to rationalize. It's because
so you can like make an estimate in your mind.
of a number. 1 over root 3. I guess 1 divided by 1.7-ish might be more achievable, but I like to divide by whole numbers. That's my personal preference. All right, so we also got, this is also the slope. That's a convenient observation that will be helpful to know in the future. All right, let's evaluate some trig so that we can like actually utilize what we've just established, what we've just defined. Really. It's like sine of pi over 6.
Sine of pi over 6. I'm going to use my pencil trick thing where I make a pi over 6 and then think about how far up it is. And so it looks like that's 1/2.
Up y 1/2. Nice. Boom. And if we plug it into the calculator, you're going to get 1/2. If you're in the correct mode, radian mode. If you're in that other lamer mode, it's going to assume that you have like 0.5 degrassis, which is going to give you a completely different number. All right, cosine 5 pi over 6. Let me try this one. I'm imagining where in the unit circle.
5 pi over 3, not 6.
Oh, thank you. 5 pi over 3. You know, I'm going to draw myself a little picture. Never hurts to draw a picture. 5 pi over 3 is down here. And it's cosine. I want the x coordinate. And because I've done this so much, I know my options. 1/2 root 3 over 2 or root 2 over 2. And this is the smallest of those three. This is also 1/2. Sweet. What do you want to do for secant?
Well, secant, I have a negative pi over 6, so I can just think that that's the same as like 11 pi over 6. Yeah. And then secant's going to give us 1 over cosine, because we pair up our s's and c's. And so cosine is the x. So what's the reciprocal of the x? That's like a 2 over root 3.
2 over 3.
Which we can rationalize. We can rationalize.
Yeah. For people on team rationalize, 2 root 3 over 3. Multiply the top and bottom by root 3. That's a pretty nasty number though. So maybe I'm on team Mrs. Contreras for this one.
I don't think we need to be on teams. We're on the math team.
All right, tangent pi over 4. My mind goes slope. What is the slope of the segment connecting the origin and the negative pi over 4, which is down there, which is just -1.
-1.
Boom. That one's quick. But if you're not feeling the slope trick, just what is the y over the x? And one's -√2/2, and the other one is √2/2. So that's just the same thing, the negative of something over the positive of something.
Mm-hmm.
Cotangent 6 pi, your turn.
Cotangent of 6 pi. Well, 6 pi means that we go around the circle 1, 2, 3 times, then we're back where we started. So cotangent of that is y over, no, x over cotangent, opposite.
Maybe use the slope trick.
Yeah, that's true. The slope is 0. So
well,
then,
slope is 0 for tangent.
So then the reciprocal of that is undefined.
Oh. That's just some more wizard magic. Sorry about that.
Undefined.
Yeah, so for cotangent, you can't really use the slope trick, but you can use the slope trick for tangent and then reciprocate it. And then last but not least, let me knock this one out. Cosecant 8 pi over 3. So that's equivalent to 6 pi over 3 plus 2 pi over 3. So that gets me to the 2 pi over 3 spot. It gets me all the way around plus 2 more pi over 3s. And then I want the cosecant, which is the reciprocal of sine, which is the y coordinate. So this is the reciprocal of √3/2. This is 2√3/3. So we find our spot on the unit circle, and then we use what's small, what's big, what's the medium √2/2. And maybe we need to reciprocate. I know all these reciprocals like the back of my hand. Where's the back of my hand?
You could just write these all. You could draw a unit circle on the back of your hand, and then you would know it like the back. You can. Not recommended.
But it does take some time. It does take some practice to get efficient at these. So we'll give you plenty of practice. And in fact, in past years, we've had students write code to make automatically generated sheets of trig expressions. So if you want endless practice, we have that too. At one point, there was an app, the App Club, that Blair used to have. There's no App Club right now, I don't think. But there used to be an App Club that made an app for trig. But plenty of practice will come, is my point. All right. A few more things, and then we're going to finish up this video. This is a little bit shorter than usual, but it's not super short because we've been fooling around a little bit. Find the values of 6 trig functions for these 6 trig functions for an angle theta in standard position if the point 34 lies on its terminal side. There's a lot of vocabulary there. I think we need to unpack this.
Okay, so we're looking for numbers.
So we want to know what sine, cosine, tan, cosecant, secant, and cotangent are of this angle.
Of theta, okay.
Yeah.
And then we're doing that for an angle theta in standard position.
What does that mean?
Well, we have like the way that we always draw our unit circle. We're assuming that our like positive x-axis, I guess, is like 0.
Mm-hmm.
And then when we proceed from there, we go, which direction is that? Clockwise, counterclockwise around.
Yeah, so we are starting, our angle is starting at the positive x-axis. That's what standard position means. And we are terminating at the point 34. So 1, 2, 3, 1, 2, 3, 4. Here's our point. That's not on the unit circle.
No, but it's nice because it's a 3, 4 what triangle?
3, 4, 5. Nice. I don't know why I did that. Anyways, 3, 4, 5 triangle. But we know that right triangle trigonometry works for any size triangle. If we wanted this on the unit circle, what could we do?
We could scale everything down by just dividing all of those side lengths by the length of the hypotenuse to make the hypotenuse a 1.
Yeah, so like, I guess it'd be like right here. It's kind of tiny. But okay, so the hypotenuse is now 1. What does that make the 2 legs?
3 over 5 and 4 over 5.
Sweet.
Wow, that's
So that's,
so tiny.
I know. So I think there's a few ways we can establish what the trig functions output. What do you want to do? Do you want to use the unit circle definition, or do you want to take it back to the right triangle trigonometry definition?
Well, I like the SOHCAHTOA, whatever that fits into.
Mm-hmm.
Just
The
thinking.
second one, the right triangle trig.
Oh, okay.
You want to do opposite over adjacent in a right triangle. Because the other option
Yeah.
is to, on the unit circle, just pull the x and y coordinates.
Oh, that's true. Because then, yeah.
So, like for
The
sine,
only one, the only one that's slightly annoying, is tangent and cotangent.
Mm-hmm. Yeah, I think it is superior to use tangent in the larger triangle.
So maybe we can do those first.
Yeah. You want to do a tangent? Well, I've written 4 over 5. I'm not going to take it back. But
okay, that's
what would the tangent be of this angle?
Tangent would be 4 over 3.
4 over 3, and I'm going to reciprocate that for cotangent.
Reciprocate.
And then let's get these. I guess both ways work. I mean, it just depends on what you're given. It looks like you're given the larger unscaled triangle, so maybe that's what we do use. But I'm looking down here at the x and y coordinates since I have it. Cosine's going to be 3/5. It's the x coordinate. Cosecant's going to be the reciprocal of sine. Secant's going to be the reciprocal of cosine. We were never given the angle.
No.
What were you going to say? Sorry about that.
I really like how you organize this, Mr. Kirk, where you set up like all of the things that you were asked about, and you kind of put it in a way that makes sense. Where you paired up like the sine and the cosecant, you paired up the cosine and the secant, but you also put like sine, cosine, tangent in an order that generally makes sense, because that's the order that we tend to think about them in that order. So it's a nice, like, it's a fake chart, but it's a nice chart.
Yeah. So I could like go down here and then do, I think what you're saying. We're still looking for the 6 trigonometric functions of some unknown angle. I do want to go back to just reiterate the fact that we never actually figured out what this angle was. But all the trig functions are intertwined in a way that might lead to the fact that you don't need the angle. We're down here. And you like how I just wrote down, and I was even more compartmentalized, I guess, but I wrote sine, cosine, tangent. Then I wrote the reciprocals. Is this what you're talking about?
Mm-hmm.
Then I wrote some parentheses.
It was very thorough. It was like you were parsing code in your brain.
All right, so we don't know what this angle theta is, but we believe that we can establish what all the other trig functions ratios should be.
Well, we know cosine of theta is 1/7 from the problem. So,
but it says
easy.
It says cosine of theta is 1/7. I think I have an issue with that, because let's go back to the unit circle. What is cosine? Our new definition of cosine.
Cosine is the x value.
The x value. So here is 0 at the origin. Here is 1 over here at the coordinate 1, 0. There is some number in between here that is 1/7.
Yes.
And maybe it's like right here, for all intents and purposes. It's like right here.
That's pretty good.
So we need to figure out we don't necessarily need to figure out, but this angle way up here between pi over 3 and pi over 2 gives me 1/7.
Mm-hmm.
But there's a second place on the unit circle.
Mm-hmm.
Between 3 pi over 2 and 5 pi over 3, where the x coordinate is 1/7.
That's true.
In every rotation of the unit circle, there are 2 places where cosine is 1/7.
It's okay, though, because the problem tells us that we're looking at the 4th quadrant.
Okay. So it lies in the 4th quadrant. So there are 2 pieces to these problems. The output, of course, but also we need to know which angle of the 2. All of these have 2 answers. Even for tangent, there are 2 places on the unit circle where the slope is whatever you give me. If it's in the 1st quadrant, there's a similar spot in the 3rd quadrant. So I'm going to draw myself a picture. Pictures are worth 1,000 words. In this case, 6 trig functions. And we need to be down here. Can you label this triangle for me? With its side lengths?
We get a 1/7.
Okay.
Or should we do it not like that?
Well, there's another freebie. Don't get rid of the 1/7. There's another freebie. What's the hypotenuse?
The hypotenuse is 1. So that means that we have 1/7 squared plus this side length, which we were going to call it opposite with a curly O.
I'm going to do some wizard magic and make this appear. Boom.
And then that equals 1. So we have 1/7 squared plus this O that we don't know squared equals 1. So
More wizard magic.
Boom. So O squared is, what's 1 minus 1/7 squared?
It has to be 48 over 49.
All right.
Right, because it's going to be 49 minus 149.
Sounds good. And then we got to break that out. Should, I guess, a vaguely green flag, but I don't think we will fret too much about it. And bam. So I'm thinking because we have a length of a triangle and we know which quadrant it's in, we don't need to be too pressed about keeping our signs super straight in this step. What do you think, Mr. Kirk?
So we don't need our signs super straight in this algebra, but that side length there that we don't know yet, O, which we do know now, that's a coordinate, right?
Mm-hmm.
And it's down. So
then,
while there should be like a plus or minus thing going on here, and we should choose the minus for this. We're in the fourth quadrant.
So we have, I can label the coordinate. Bam.
Boom. Boom. So now we can just start pulling coordinates to evaluate sine, cosine, and tangent and its reciprocals. It's like sine. That's the y coordinate. You want to write these?
Sure.
Bam. I don't think Gandalf says bam when he does magic, though.
Oh, what does he say?
You shall not pass.
I don't know how much we should say that.
What?
I don't know how much we should say that to our students, though, Mr. Kirk. They might get worried.
I was specifically talking to the Balrog.
The Balrog?
Is it Balrog? I've been calling it the Balrog.
I think it's Balrog.
Yeah. Well, J.R.R. Tolkien likes to make up ridiculous words, so.
Speak friend and enter. Maybe we should put a password on this. And then what do we have?
Tangent's gonna be a slope. Slope is gonna be annoying here, so I think we should just divide.
So
although
like
doing division's not that bad, right? Because the sevens cancel. Yeah. Chop chop.
Chop chop.
What would Gandalf, or well, I guess, what would a Lord of the Rings character say? Maybe a dwarf would say chop chop.
Maybe. I feel like they just do like. I
love Gimli.
He's pretty cool.
He's pretty great.
He's very cool. I really identify with him in terms of running. Dangerous over short distances, but I am lost on cross country.
Boom. I think another thing we could have done is the let's scale it up to a triangle who doesn't have fractional sides.
That's
if
true.
we multiplied everything by 7, we would have had a hypotenuse 7 and legs of 1 and root 48, and we would have gotten the same answers.
That's true.
But the key is we need to recognize that this is in the fourth quadrant, which is going to change the value for sine and cosecant and tangent and cotangent, because the slope is negative in the fourth quadrant and the y coordinate's negative in the fourth quadrant. I think there's one last thing we can do in this video that might help people.
What do you think it is?
I'm going to go ahead and add a page. And let's just real quick establish in what quadrants are sine positive. And in what quadrants are cosine positive and tangent positive. The reciprocals get tagged along. But here I am. Here are our 4 quadrants. And I could do a better job on that second one. Yeah, that's good enough.
Sure.
All right, so when are the trig functions positive? So which trig functions are positive in the first quadrant? Well, let's talk just about sine, cosine, and tangent.
I think all of them, right?
Yeah, because the x and the y coordinates are both positive in the first quadrant, and the slope is positive. So all of the trig functions are positive in the first quadrant. How about the second quadrant?
Well, our x values are now negative, so that means that cosine
Cosine is going to be negative now, right? And the slope is negative, so tangent's going to be negative.
Yeah.
So the only one that's positive in the second quadrant is sine. How about the third quadrant? We're thinking x, y coordinates, and slope.
So the x coordinates are negative, the y coordinates are negative, but negative over negative is positive. So that means that tangent, and I guess cotangent, but
Yeah. But those all get tagged along. Sine and cosecant are positive in the second quadrant. Well, I appreciate you adding the Roman numeral.
we just did this today in maps. Like we established the Cartesian plane. It was
Sweet.
exciting. Anyway.
Also, so we have all sine, tangent, and then the last quadrant, x is positive, so cosine
X is positive. Mm-hmm.
Y is negative, so sine's negative. And tangent is a negative over a positive. So this is just cosine. The first quadrant all, second sine, third tangent, fourth cosine. There is a acronym to help us remember this. And I actually hate it. I hate the acronym very, very much. I'll briefly explain why in a second. But I'm always looking for a better acronym every year. I had a good one last year, but I can't remember what it was. So it was good, but it wasn't memorable. So I'm looking for both a memorable and a awesome acronym for ASTC. The standard one is all students take calculus. But that's just like not true. That's why I'm not a fan of it. All students take calculus. So I'm looking for a better acronym. This is the one that I was taught. All students take calculus. But not all
I
students
don't
take
think I ever
calculus.
learned this.
Did you ever learn like ASTC, or did you just like skip that completely? It's not necessary.
We might have just skipped it and
Yeah.
just like remembered things.
Yeah, maybe your teacher was like, yeah,
But
this is really
okay.
dumb. Why are we worrying about this? All students take calculus.
Or like anyone should try ceramics.
I like that a lot better. But the problem with that is I'm not going to remember that in 365 days. Looking for something. And this is just me asking for the creative minds of 120 people. Can anyone think of a better acronym for all students take calculus, ASTC, besides this like not true statement?
Oh, it could be a come up with brainstorm maybe like 5 or 6. That could be a journal entry.
Maybe we'll pick the winner and then they win a prize at some point in the distant future. All right. I think we have gotten the ring to Mordor, to Mount
we?
Doom.
But the ring is mine.
Where'd you go? We need words of wisdom.
No, I disappeared. The ring is mine.
The ring is. You have to sound like.
No, just kidding. We should destroy the ring. Let's just
destroy the ring. Destroy the ring.
Scott.
It is the source of all destruction and doom and sorrow in all of the land.
It's no bueno.
All right.
Wait. Let's see if I can get this going again.
If you're talking, I can't hear you.
I'm not talking yet.
Oh, okay.
No. I lost my hat. What kind of wisdom does Gandalf have?
Probably a lot.
Well, I think we should read the quote from I wish the ring had never come to me. I think it's very appropriate. Oh no. Okay. So Frodo says, I wish the ring had never come to me. I wish none of this had happened. And then Gandalf says, so do all who live to see such times. That is not for them to decide. All we have to decide is what to do with the time given to us.
That is very.
And in light of everything that's going on, we don't get to choose when we are alive, but we are gonna do what we can with the time that we have.
You read it one more time for me.
Sure. I wish the ring had never come to me. None of this had happened. So do all who live to see such times, but that is not for them to decide. All we have to decide is what to do with the time that is given to us.